algorithm which takes an input of our parameterized problem, which typically consists of two things, an input and a parameter, and we want to produce an equivalent instance whose size is bounded by some function of k. Okay. So equivalent means that this is S if and only if this is S. And so at the moment our aim is not really to solve the problem, but to spend only polynomial time to produce an equivalent instance whose size is a function of k, because if you really want to solve it, you can use some algorithm to solve this. Now everything is a function of k, so you can get your FPT algorithm out of it. So we saw a very simple kernelization algorithm for vertex cover, which is due to bus. So it's often called, this particular rule is often called something like a bus rule, where if you have high degree vertex, if you don't pick it into the solution, you have to pick all its neighbors and you go over your budget. So you need to pick that vertex and keep picking them up, and now you have a new budget, k minus whatever you have picked, and then we can argue that just these two rules are enough to argue that the number of edges is order k square, number of vertices is order k square. Like, okay, so then we said, okay, vertex cover is essentially a two heating set problem. You have a family universe and a family of two sized sets, and you want a subset which intersects every set in your family. Then this idea can be generalized for three heating set. So if I write this as two heating set, for three heating set, we got a kernel with order k cubed edges and vertices. Okay. Essentially using this rule, but maybe one more time, you look at pairs of vertices that appear more than k times, do something about it, and then you look at a vertex which appears more than k square times included in solution, then you argue it's k cubed. And then I said this is useful, for example, I just want to correct a couple of things I mentioned. One is we said FES in caudal graphs. Can be modeled as a three heating set. That's true because in caudal graphs, hitting all cycles is the same as hitting all triangles. So you just go and collect the universe will be your vertex set, and the family would be the vertex sets of triangles in the graph, which you can find in n cube time or something. Collect this family and then apply my three heating set kernel, I'll get k cubed. So it's not, I should not say edges here when I get to three heating set. This is k cubed sets and elements, right, because it's not a graph problem. And the second thing I was suggesting was feedback vertex set in tournaments. Again, you know it's the same as hitting directed triangles. Collect this family of vertex sets of triangles, hit them, use this three heating set. So now a couple of points on set. One is that it turns out feedback vertex set in caudal graphs is actually poly time solvable. It's really not an NP complete problem. You can use some tree decomposition and various things to solve it in polynomial time. So why is coming up with the kernel for a polynomial time problem not so great? And so what? It's polynomial time solvable. So I have xk, which I produce an equivalent x prime k prime in polynomial time with k cubed sets, k cubed elements, or k cubed vertices, k cubed edges, whatever. Why is it not such a meaningful exercise if the problem is solvable in polynomial time? Yeah. Kernel, true. But so the answer is that anyway in polynomial time you can solve the problem. But I am giving you a kernel. The goal is to get a kernel of a certain size. It may still be interesting. Polynomial in n and k. The input size and k. So I will, okay, I mean you are almost there, but I just want this one missing piece. So see, if the problem is polynomial time solvable, then what sort of a kernel can I get? That could be very large. It's not a function of k. Yeah, some constant size kernel, right? I solve it in polynomial time, and if the answer is yes, I produce a graph with k sized solution for whatever your k, constant size. And if the answer is no, I produce a graph with no instance, a trivial S instance or no instance for the original graph with constant size, independent of n, independent maybe even k size or something. So if the problem is polynomial time solvable, you can actually produce constant size kernel. So all this exercise was not that meaningful, but it was still an interesting exercise to go through these rules. The second point is that in my definition, I really wanted a problem. I mean, I said it towards the end of the last lecture, but I want to emphasize that in my definition of kernel, I want to produce an instance of the same problem finally. Okay. So if you are dealing with vertex cover, I produce another vertex cover instance and say, okay, solve this. Now this graph has at most k square vertices and k square edges. That's what we did. But here we are not doing it. If you want to solve feedback vertex set in tournaments, I create this hitting set instance and then apply my kernel and I produce a hitting set instance which has k cubed sets and k cubed elements of the universe. But I really want a tournament if I have to strictly follow this definition, right? Because you are given a tournament and k, I want to produce another tournament and k prime whose size is function of k. But what I produced is some instance of some other problem, in this case hitting set, which has some function of k elements and universe and so on, right? So how do I get, so that's really not a kernel. What we, using this, I sort of said you can get a kernel for this, but not just immediately applying this. So there are two ways to get around it. So what can you do? One is, so I might add to get a kernel, okay, for FES, right? So what do? We take the FES problem, convert it into 3 hitting set, kernelize it, and you get a 3 hitting set instance with k cubed elements and k cubed sets, right? Finally, I want to get a tournament instance. So what should I do? One thing I can do is, there is a polynomial time reduction from 3 hitting set to feedback vertex set in tournaments. Why? Because both are NP complete. This is NP complete. This, in particular, feedback vertex set in tournaments is NP complete. I did not say it, but can actually prove this. So since feedback vertex set problem is NP complete and 3 hitting set is an NP, by definition of NP complete reduction, I can take the NP hard reduction and get a feedback vertex set in tournament instance. Okay. But what happens to the size of this tournament in this whole process? Well, it's a polynomial in k cubed, exactly. So it may not remain as k cubed, but it's at least poly in k. That much you can guarantee. If this reduction is so nice, it's linear time reduction, then it will be nice, k cubed will go to k cubed and I will get it, but I don't know. Otherwise, all I can guarantee is that there is a polynomial time reduction, so that might take this. So if you are happy with a polykernel for a feedback vertex set in tournaments, this thing works, this machinery works. Basically, we convert it to a different problem, use its kernel and then do an NP complete reduction, come back to my original problem. But in the process, I am only guaranteed a poly-sized kernel if this is poly-sized in K. Okay. So this is one approach. The second approach I would say is, so we applied some kernelization rules to get here, right? So if a pair appears in more than k sets, then replace it by something, right? So apply it directly on feedback vertex set instead of converting it to 3 hitting set. Take the feedback vertex set instance and sort of apply the 3 hitting set reduction rules on the FVS instance without converting it into three hitting set instance. I am not claiming that this is always possible or it's trivial. You may need some gadgets, because one rule will say, if a pair appears in more than k triangles, then replace these triangles by one edge or something like that. Now, how do you do this and still maintain the tournament structure? You may have to play around with some gadgets to do that. So that's one possible approach. I'm just giving you a general approach. When you have this kind of, you convert it to a problem and you want to use the kernel for the other problem. The third approach is try and generate this yourself, right? Finally, what you have is a 3 hitting set instance. That means a family of sets with triple sitting there of total size k cubed, right? Can you convert that into a tournament where these triples will correspond to triangles? So if you can do this directly without resorting to NP hard reduction, you don't know what it does to k. If you can hand design this reduction, then that's another approach, right? Okay, so I am not going to do any of this, but I want you to really play around with this, particularly second and third approach. See whether you can get your k cubed vertices and edges kernel for feedback vertex set in tournaments by essentially simulating the rules we applied on the 3 hitting set. Okay, or just apply it, finally you get your kernel and do some conversion. So I'll leave this as an exercise. And there is no general thing. This is a general enough theme if you are happy with poly in k kernel. But if you want to be really tight, then you want to design some reductions specifically for the problems. Okay, good. So now yeah.
Is it number of triangles is something like quarter n squared.
Easily, meaning in polynomial time. As opposed to, how many can there be?
N cubed.
Okay, yeah. So I doubt whether n square will buy you something better. No, I'm not sure. I don't know, but I doubt.
There's n square root and u square root.
The number of triangles n square root.
Less than n square root, and then you can, if you can solve it in polytime, then you do that, or else you can get a kernel.
But that's only for triangles, or you meant the number of edges? What did you?
Triangle.
Okay.
You said less than n square root n. Then
Yeah.
if you can do it in polytime, do that.
Otherwise,
Otherwise, you can. This is after some. You apply some.
so if the number of triangles is greater than n square root n, what do you want to do?
Okay, this check you do after you first you find out for each vertex the number of edge disjoint triangles existing. If that is at least k plus 1, then you delete that vertex and so on.
Yeah, so that's what I really mean here. That's the kind of rules you want to do this.
In the end, you get the tournament has like kn edge disjoint triangles. So if the number of triangles is greater than
They're not really edge disjoint. You can only say one edge participates in at most k triangles.
yeah, but you can still say that kn will be greater than or equal to.
We can talk about it. Yeah, I'm not very sure. So let's see how I would generalize this for a deheating set, right? Kernel for so recall the kernel for 3 heating set was if a pair appears in more than k sets, then we said that one of these elements has to be in the solution. So you replace those sets by this pair. This is one reduction rule, and then after that we argued that if a vertex appears in more than k square sets, then that vertex is forced, and then we argued k cubed kernel. But if I want to do this for deheating set, well, we could keep doing this. Instead of a pair, you will just look at a d minus 1 tuple appears in more than k, then you know that that has to be picked into the solution and so on. You can get a kernel like that, but there is a more direct way of getting it using what is called the sunflower lemma, which is also an independently a useful combinatorial tool. So let's do that. Right, this is due to so what does this say? So let U be a universe, F be a family of d-sized subsets of U. If cardinality of F is greater than Okay, what is a sunflower, right? So what this says is that if you have a family, large enough family, then there is some structure in that family. Okay, what is a sunflower? Sunflower is something which looks like this. So it's okay. So S if all these sets intersect at a core and if you have F1, Fi, Fj in S, and every pair actually is, they intersect only at this pair. Okay, so as the picture says, if you look at, so F is a big family of D-size subsets, and some subcollection from F, some collection of sets is called a sunflower if they have a common intersection, let's say Y, and these are called petals, and which is basically the rest of the set. So an F would be something union Y, and if you have Fi and Fj, Fi is this and Fj is this, their intersection is only Y. They are pairwise, otherwise disjoint. And Y could be empty. Okay. So is it clear? Is the statement of the lemma clear? D factorial into k minus 1 power d. What is this k? Cardinality of S is k. So if you have so many sets, then I can find a subfamily from this family where they all intersect at Y is called the core of this. There is one set in which they all intersect, and otherwise they are pairwise disjoint. And the number of such sets is k. The claim is that such a subfamily exists. Okay, so D is greater than or equal to 1. Okay, so is it clear what? So if there are a large enough family of sets from this universe, then I am going to get some sunflower with k petals. The proof is by induction on D. When this works, even if the sizes of the sets are at most D, and you can fill it up with some dummy elements and make them size D, but let me state it for D sized sets. Okay, so what does it say when D is 1? Right. So when D is 1, what is this saying? I have a family, all these sets are distinct, okay? No pair of sets repeat. Then it's a family of singletons, And D is 1 means I have strictly more than k minus 1 of them, so there is at least k of them. So note that if you have a family of pairwise disjoint sets, that is a sunflower with empty core. Okay. So in particular, if you have, so for D equal to 1, every pair is disjoint. So true with y equal to empty. Take your family has more than k minus 1 set, so it's at least k sets are there. Pick any k sets, they are pairwise disjoint with the empty core, you have a sunflower with k petals. So when D is greater than or equal to 1, or greater than or equal to 2, okay, we're going to assume it true for D minus 1, right. So induction hypothesis, assumed true for up to D minus 1. Okay, so pairwise disjoint sets are good. So let's find a maximal collection of pairwise disjoint sets. Let's call this some B. And this is easy to pick. I pick some one set, it's a maximal collection. So pick a set and then I run through my family. If I find a set that intersects this, I ignore it and move on to the next set and find such a maximal pairwise collection. So every new set, make sure it doesn't intersect with any other sets I have picked. So in polynomial term, I can collect this family of pairwise disjoint sets, right. So if B is greater than or equal to k, then if B is greater than or equal to k, we are done. Produce this as a solution, right? Because I want this is pairwise disjoint sets are always sunflowers with core empty, so we are done. Okay, so therefore B is less than or equal to k minus 1, and let's call this as some set S, and cardinality of S is at most D times k minus 1. So now let's look at my family, right? Let's say this is my sets B and these are the remaining sets. So I have picked some D times k minus 1 elements here. What can you say about each of these sets? Any set here will intersect with some set here because it's a maximal collection. So any set here intersects with some set here, right? So what's a nice way to say? So let me just create this kind of a function. Okay, so this corresponds to, look at this function. This corresponds to every set in my family. Okay, every node. And here this is elements of S. S is, remember, the union of all these sets. This is my S. Okay. Now if you pick some set in the family, at least one element appears in S. That's what we figured, right? For all these elements, sure, no problem. But even for all these sets, if you pick any set, it intersects with this, some of these sets, that means that some element is in S. So I associate with that F some arbitrary element that belongs to that set F from S. Okay. So each set I am going to map it like this. and so on. So the claim is that there exists a U in S such that U appears in at least cardinality of F by cardinality of S sets. Right? So I have partitioned my family into size of S many sets, right? I have partition. So this set goes to this element if this element is in that set. Of course, there may be many elements of S into that set, but I pick arbitrarily one and map it to that. Similarly, this set goes to this element and so on. So now, see, F is very large, right? F is at least d factorial into k minus 1 power d, whereas this S is small, right? Whereas F is large. So a lot of elements get mapped to one element, lot of sets get mapped to one element. So there exists an element that gets mapped by several, at least that many sets. That means there exists an element of S that appears in at least that many sets. Okay, what is this number? Since cardinality of F is greater than or equal to d factorial into k minus 1 power d, and cardinality of S is at most d into k minus 1, this is equal to d minus 1 factorial into k minus 1 power d minus 1. So I look at, let's say this is that particular element, and look at all sets that contain that element. Now work with that. The number of such sets is very large. Now apply induction on that. They all have this particular element, but by induction, you will get a sunflower with k petals here because d minus 1. They are all, if you remove this, you remove this element from those sets, they are all of size d minus 1 now. Apply induction, there is a k petal, sunflower with k petals. In that set, if you put it in, it gets into the core because it is part of every element in that set anyway, in that family. Right? At least so many sets. Apply induction. On sets containing that element. Okay, questions? Now let's see how this is useful for our kernelization. Okay, so typically this is a common theme in kernelization is you come up with some very nice structural result that will lead you into a way, some pre-processing rule, and you can get a kernelization. So what is that? Yeah.
Is this exactly Y or subset of Y? The faint section change.
Exactly Y. They cannot be subset. Y is part of every set anyway.
Yeah, every set of
Y is in the intersection of every set here. So they Y is common to everything, and this is saying nothing else is common. Even if you pick, not only nothing else is common to everything, any pair of them are otherwise disjoint. Their only intersection is Y. Okay, so now let's use this lemma for our kernelization. So why is this useful? Remember, we want to hit every set by a k-sized subset. So why is the sunflower useful? So if you have a large sunflower, what can you say? right? So if there is a sunflower with k plus 1 petals, then what? So I have this huge family of sets and I want k sets to intersect every set. Somehow by applying sunflower lemma I managed to get a sunflower with k plus 1 petals, right? So what can you say? This is like the bus rule. So
There should be some element in the core.
there should be some element from the core into the solution. Exactly. Because if you don't pick any element of core, who will hit this set? Some element from here. Who will hit this set? Some element from here. But remember, these sets are pairwise disjoint. So you have to pick one from here, one from here, one from here, one from here, one from here. That's k plus 1. And you are looking for a k-sized solution. This exact generalization of this high degree rule. So all this is saying is in this family of sets, so then y intersection a k-sized solution is non-empty. Any k-sized solution must intersect y, because if you don't intersect y, you have to pick k plus 1 elements to in your heating set. So this suggests a reduction rule. What is the rule?
Find the sunflower. If it is find the k plus 1 sunflower and
Add the core to your family. Okay. There is only one little problem. Reduction rule. Find a sunflower of size k plus with k plus 1 petals. If exists, then add y to my family. We'll come to that. Okay. So first, can you find the sunflower? That's one question. There's another important question when it comes to kernelization. What progress have you made?
size reduction by k.
Where you actually added, increased it,
No,
the family.
deleted the whole sunflower.
You didn't tell me that. Okay. Add y to f, delete the sets forming the sunflower. So what this is saying is, if you manage to find the sunflower, remove these sets and replace it by just your core, because you have to hit it. So it's an if and only. So you have to hit it anyway. That's what we argued here. And if you hit it, you have hit every set anyway. So you don't need to necessarily put those sets. So remove those sets, put the core into it. So now we have removed k plus 1 sets or more and replaced it by one set. So your family size comes down by k. Okay, so that means you will not do this forever. This process will stop. Okay. So now let me, well, this lemma guarantees a sunflower. So let me add, if size of f is greater than d factorial times k minus 1 power d, then find the sunflower with k plus 1, is add y to f. Delete the sets forming the sunflower. Okay. Okay, so now can you find the sunflower, right? Yes, can you? Take the proof, can we not convert the proof into an algorithm? What did we do? First step of the proof is find a maximal collection of pairwise disjoint sets, polynomial time. Take a set, just run through your family and compare it with the sets you have collected. As long as you intersect, you throw it away, otherwise add it to my family. Collect that. That's polynomial time. And if that itself is a good solution, you're done, you got a sunflower. If not, what did we do? We argued that there is some element that appears in a lot of sets. So, run through the sets you have collected and see, count the frequency of every element. Pick the one which appears the maximum number of times. That's again a polynomial time computation. Work with that family, remove these elements, and then apply indection. Okay, so we have to just go down these steps. So in polynomial time, you can find that. Polynomial in, so I should, f has this, can be found in poly in size of u, size of f, d, k, whatever. You can find it. Right? Because this is just d more than, not even k, but just d. Right? You can convert the proof into an algorithm and it will be d times size of u into size of a or something like that. Okay, good. Now when do you actually say no? Do you actually say no? I mean, okay, you can keep giving this.
Find a set that can't be hit.
I mean, you don't have to say no, you can keep giving this. So, in fact, do we have a kernel yet already? What is kernel size? This kernel size, right? So, what is it saying? If the family size is large, you can find the sunflower and reduce it. Check again. If it is large, find the sunflower, reduce. When do you stop? If this becomes small, then that is the kernel. You have a family whose size is at most d factorial into k minus 1 bit. Actually, not k minus 1 bit, k power d, right? Because I'm looking for sunflower with k plus 1 petals. So it's k power d. So you can stop when this happens. Okay. Now coming back to my question, when do you say no? If you can find a set which can't be hit, can you? What is a set which can't be hit? If you have an empty set in the family, you can't hit it. If y is empty, what does that mean? You have got a sunflower, which means you've got a k plus 1 pairwise disjoint sets. So each set requires a separate thing to hit. So you can't hit it with k elements. So if y is empty at any point of time, you can say no. Right? So if empty set is in F, we can return no. Net, we have a kernel with d factorial into k power d sets are at most, and since each set is of size d factorial into k power d plus 1 elements. No, d plus 1 factorial into k power d elements. So this is some general theme of kernelization in some sense, that if you have some nice structure, some reduction rule is applicable, you can keep apply it, and otherwise you get a bound which is just a function of k and d, it does not depend on n. So it's poly in k kernel. So the sunflower lemma is very useful. Whenever you work with some family of sets and you are trying to do some problem on that, it's a useful thing. Okay, so now let's do another nice combinatorial structure on graphs, which is useful for kernels, and that takes us to what are called crowns. Okay. So recall, we started with this vertex cover kernel, which had essentially two basic rules. One was that if you have a vertex with very high degree, you have to include it in the solution, and that generalizing this came this far. The other rule was if you have a degree 1 vertex, you better include its neighbor into the solution, you can get rid of it. Oh, I did not put that rule. That was an isolated vertex rule, but that's another nice rule, right? So if you have a degree 1 vertex, if you have a graph with this thing, then any vertex cover should cover this edge. So it should contain one of these vertices. Why do you want to pick this vertex? You basically pick this vertex, delete it from your graph, add it to your solution and move on. This is one nice simple rule, and what you get is an equivalent instance, right? Because if it does not contain this vertex, it should contain that. Remove it and put this, and it still remains vertex cover of the same size. This rule can be generalized to what is called a crown reduction rule. So what is a crown? Okay, another nice combinatorial structure based on matching. So let G be a graph. We are working with undirected graph. Okay, so let me draw a picture so you know why it's called crown, right? So this is the head, and this is my C, and this is the remaining. This is how the graph looks like. So I have partitioned my vertex set into 3 parts with the following property. Okay. C and H are non-empty. This is the more important, okay, and T Okay, so this is, I have a partition of my vertex set into 3, C, H and R. This induces an independent set. There is no edge with one endpoint here and another endpoint here because neighborhood of C is contained in H. Okay, so the neighborhoods of C are all entirely sitting inside. More importantly, there is a matching that saturates every vertex of H. There is a matching in which graph? In GHC. So if you look at this graph, I mean this contains only all edges between H and C. So for example, if you have an isolated vertex in the graph, what is the crown? This is my crown. So this is my C, this is my H, this is my rest of the graph. Right? I mean, this is not a triangle. I'm talking about this is a whole graph. Right? This is an isolated vertex. Its endpoint is the only vertex which I am going to put it in H. This is C. G of C is C and H are non-empty. G of C, there is only one vertex independent. There is a matching that saturates every vertex of H. Looking at edges between C and H, and neighborhood of C is contained in H. Okay, so crown is essentially a generalization of this structure. Why is the crown useful for vertex cover kernel? Can you think of a rule similar to the isolated vertex rule, or sorry, not isolated, degree 1 vertex rule?
H is belongs to vertex cover.
Right. You can say without loss of generality, I can include H into my solution. Why? I mean, into my optimum solution. It's not just any solution. There exists an optimum solution that contains all of H. If I find such a structure, then I can reduce the graph. Remember, kernel is all about reducing the graph, right? I can just quickly pre-process, reduce the graph by picking all of H into my solution. Why? Why do I need all of H? Because there is a matching saturating H. If I want to cover edges, if I want to cover all the edges across H and C, clearly you need at least cardinality of H many vertices to cover them, because there is a matching that saturates this, and they are covered by some vertices here or some vertices here. Nobody else is going to cover them. Why do you want to pick edges, vertices here? You might as well push them here. It's exactly like the way we argued here. Okay. So there is a simple reduction rule if I find a crown, which is just to include H into my solution, delete H, C will become isolated, delete C, and reduce the budget from K to size of H, and continue. Okay. Now the question is, how do I find a crown? When can I guarantee such a crown? Right. So like we had the sunflower lemma which says that if you have a large family, you can find a sunflower, use that to reduce. We want to say something like, if you have some structure in the graph, there is a crown which I can find and reduce, right? So whenever I cannot reduce, what I have is a kernel. That's the way we want to argue. Okay, so let's state the theorem. So we are going to use something we learned in the first lecture about in a bipartite, several times. In a bipartite graph, maximum matching and minimum vertex cover are the same. We can find both of them in polynomial time. Okay, that's going to be useful. Okay, so what do we do? Right. So let me write the theorem. So what was the kernel size we had from the burst kernelization for vertex cover? K square. K square vertices and K square edges. This is going to give you a big reduction now. So what is this? If your graphs has greater than 3K vertices, then G has a crown and it can be found in polynomial time. Right, so my B is N and E is M. So this is the time to find maximum matching in a graph, okay, bipartite or even general graph. So that's what you're going to use. So this time is not that important. You can do it in polynomial time because in bipartite graphs you can find maximum matching in polynomial time. Okay. So here it is. So I mean, if after we prove this, what kind of a kernel would we get now for vertex cover?
What's the size of the ground?
No, size of the ground is not the kernel. 3K kernel. Because what is this? See, if I find a crown, I know how to reduce it. We discussed that. So, if I find a crown, I can include the h into my solution, decrease k by the size of h. All of this goes away and work with the remaining graph, right? So, what is this saying? As long as you have more than 3k vertices, I will find a crown. I know how to reduce it. Look at the remaining graph. Is it more than 3k? Find a crown, reduce it. If it's more than 3k, find a crown, reduce it. When do you stop? If you have at most 3k vertices. So I have a kernel with at most 3k vertices. Okay, so we reduce from k square to 3k. Once I prove this, and prove the correctness of this crown reduction, which is more or less obvious, but yeah, right? Okay, so how does this work, right? Okay, so let M be a maximal matching engine. So that's my M. I find a maximal matching. Maximal, so it's pretty easy. Maximum requires so much work, but maximal is even easier. Pick an edge, delete all edges incident on its endpoints, just go find another edge and keep doing it, right? So this is my M. What can you say about the remaining graph? There are no edges here. Right? So this is independent. Let's call this I. Right? Because if I had an edge here, I would have added to the maximal matching. So this is independent and this is a maximal matching. Wait. Okay, now I have to modify this. Then either G has a matching of size k plus 1 greater than k, or I will produce a crown. Either I will produce a matching of size more than k, or I will produce a crown. Okay. But from the vertex cover point of view, a matching of more than k is also good, right? What can you say? It's a no vertex cover of size k. If you find a matching of size more than k, you can right away stop and say it's a no instance. There is no vertex cover of size k. You produce a trivial no instance kernel, right? So either I'll say no, or I'm going to find a crown which is useful to reduce. Okay. So if M is more than k, we are done. Because one of my goals is to produce a matching of size more than k. If M is greater than k, we are done. Okay. So else, so otherwise, so let's call Bm vertices that are endpoints of M. Sorry?
The condition is that there will not be something like 2k because depending on maximum. And maximum matching might be, in the worst case, something like half of the maximum matching.
So what are you saying?
So I think always find the, no,
I will,
okay.
I am claiming what I will find. So far I have not violated anything. Either I will find a matching of size greater than k, or I will find you a crown. So if m is greater than size k, I have found a matching of size greater than k. Otherwise, I am continuing. And let I equal to v minus v of m. Okay, now I'm going to find the matching. So ignore these edges inside here. So look at this bipartite graph where one side is Vm and the other side is I. Okay, ignore all the edges inside this part of Vm. Look at this bipartite graph, there are all edges going across. Find the maximum matching in that bipartite graph. Again, okay, so here is where I am applying maximum matching in a bipartite graph. Let m prime be the maximum matching in the bipartite graph So this is a notation by this. I am just saying Vm is one part and I is another part. Ignore all edges which are both endpoints in Vm. Just look at only the edges across and find maximum matching. And as a bonus, you also get minimum vertex cover. And X be the minimum vertex cover. Okay, hopefully the definition is clear. I will keep the picture. Okay, so what have we found? We have some matching like this, and this is M prime. And I found a minimum vertex cover. The minimum vertex cover can have some vertices here and some vertices from here. Okay, maybe it just picks this, whatever. So this is my X. Okay, so this is my Vm, which has these vertices. This is my I, and I found maximum matching here, and found my minimum vertex cover. Remember, in a bipartite graph, minimum vertex cover picks exactly one vertex from each of the matching edges, right? So it picks something from here and something from here. Okay, if m prime size is greater than k, we are done. Another matching whose size is more than k, right? So m prime is also controlled. Oh, let's also assume that G has no isolated vertices. Okay, so this is the story here. Now, if, okay, similarly we have V of m prime, endpoints of, no, I don't need it. Why bring in the notation? Now it's possible, so I have a minimum vertex cover. It's possible that the minimum vertex cover is entirely in I. If X intersection Vm is empty or non-empty, I don't know. So this is the minimum vertex cover suppose it manages to pick everything from here, then I claim it must be the entire I. Why? Very good. Because there are no isolated vertices. So every vertex in I has some edge going across, because this is independent. There are no isolated vertices. Every vertex here has some edge going across like this. Who's going to cover that if you don't pick that vertex? Because you said X intersection Bm is empty. Therefore, X, note that, okay, so X is equal to I, but we also know that this is the same as X, right? Because in a bipartite graph, minimum vertex cover and maximum matching sizes are same. So X is less than or equal to K, so this is less than or equal to K. So what does that mean? Do you see a contradiction here? Because we assume that I have more than 3K vertices. But what I have at most 2K vertices here, at most K vertices here. That's all the total number of vertices. So I find the maximum matching across, and suppose the vertex cover does not intersect of this bipartite graph, does not intersect this, the vertex cover size must be equal to this, but vertex cover size is at most K because the matching size is at most K. So that means size of I is at most K. So this has 2K vertices, this has at most K vertices, totally I have only 3K vertices by assumed that this is where we use the fact that it is more than 3K vertices. Now I am going to produce you a crown. What's my crown? So H X intersection Bm, this set is my head, and all the other endpoints of the matching edges will become C. Endpoints of M prime in I, whose other endpoint is in H, and R is B minus H minus. Now let's argue that why is it a crown? Okay, that should be fairly obvious, right? So what I am saying is X intersects here, so that X is going to be my head. X has these, and they all have edges of M prime with other endpoint in I, so that's going to be my C, and the rest of this is R. So let's go through the conditions of crown. C is independent, sure, because the other endpoint is sitting in I, so that induces an independent set. There is a matching that saturates the head. This is the head. Sure, by definition there is a matching that saturates all of this. There is no edge like this is the next condition. Why? If there is such an edge, who will cover that, right? So if there is an edge from C to R, that, so this is my C, right? Essentially this is my C. So this is X, this is my C. Its only edges are to this side because this is independent. And if it has an edge to somebody here, who will cover that edge, because this is not in X and this is not in X. So, X is supposed to cover it's a vertex cover for this bipartite graph. So there is no such edge between C and R. So it's meets all the definition of my crown. It's non-empty because I assumed H, this is non-empty. So we got a crown. And what effort did I do? I have to do a couple of matching, a maximal matching and then a bipartite graph maximum matching. Get a vertex cover out of it, and then the rest is simple, probably linear time. Okay. So let's see a couple of applications of this. So this is very general, not just for vertex cover, right? The crown, this statement doesn't say anything about vertex cover. This statement says that if you have a graph with more than 3k vertices, either I will find a k plus 1 sized matching or a crown. Independent, nice theorem which is useful for a lot of applications for kernelization. The way we apply it for vertex cover, so if V of G is more than 3k, apply theorem. If you find a matching of size greater than k, produce a trivial no instance. Else get a crown. So B G becomes G minus H. My S, the budget K becomes K minus size of the H. Continue. Right. So just go back here. The resulting graph size is more than 3k. Find a crown or matching. Keep doing it. We stop at 3k sized. But we get k square edges though. But still, but the number of vertices has come down to pretty small. Okay. So this is very nice. It says that I have a million vertex graph where I want to find out whether there is some vertex cover of size 50. Then in polynomial time, by applying a couple of matching algorithms, I will reduce my graph size to at most 150. Or along the way, I might say no. Solve the problem, or now I can do some pre-processing here. Okay, let's do one more application, and that's for MaxSat. So what is the problem? Given f in CNF form, my parameter is k. The question is, there an assignment? Okay, n variables, m clauses that satisfies at least k clauses. We saw a kernel last time, or some 2 lectures before. Remember that? What was the size of the kernel? So, first observation is that we can assume the number of clauses to be yes, there is 3 to the power something, but what was that? Number of clauses
So first you bound the number of clauses
by how much?
2k.
2k, exactly. Because if you want to satisfy at least k clauses, and we use the observation that there is always some assignment that satisfies at least m over 2 clauses for a CNF SAT. So, if k is less than m over 2, you can stop and say yes, it's an S instance and move on. So, if k is more than m over 2, that means m is at most 2k, right? That's a trivial bound. Then we did some encoding to bound the number of variables to be at most 3 power m, which is at most 3 power 2k. Basically, we said for every variable in this 2k variables, 2k clauses, check whether it is present purely, negated or not present. That gives you a 3-way encoding, and if 2 variables have the same encoding, you can get rid of it somehow with some reduction rule. That bounded the number of things to 3 power 2k. Now, using Crown, we will bound this to at most k. Okay, so it's such a powerful rule. Okay, so again, what we need, I mean, apart from this Crown thing, we need Hall's theorem for bipartite graphs, and some little. What do you get in Hall's theorem, right? If you, what is Hall's theorem? I have x, y, I have a bipartite graph. I have a matching that saturates x if and only if has at least that many neighbors, right? So, there exists a matching saturating x if and only if there exists, if and only if for all set S contained in X, the neighborhood of S size is greater than or equal to cardinality of S. That's a very famous, powerful theorem for when do you have a matching that saturates every vertex of X. If for, I mean, clearly every subset should have enough neighbors, that is a necessary condition. What Hall's theorem says is it's also a sufficient condition, that for every subset has enough neighbors, then you can match every vertex here. A consequence of this is that, well, again you can use some max flow min cut kind of a thing to show the following, that either there is a matching that saturates X, or there exists a set contained in X such that n of S is less than cardinality of S. Okay, you can take that proof of Hall's theorem and convert it, or use some flow arguments to get this. So, either I will give you a matching that saturates every vertex of X, or I will give you a witness set S who does not have enough neighbors. Okay, so we will assume that one can also say that this is inclusion wise minimal. Okay, which means that S has this property, but every subset of S has enough neighbors. We can find that also in more or less the same time. So, in order m root 10 time. So, now how do I apply it here? So, what we will do is we will construct this following bipartite graph, where I will have my variables and my clauses. C1, C2. Okay, and draw an edge. I will draw an edge from xi to Cj if xi or xi bar is in Cj. Okay, so that's my edge relationship. I have this bipartite graph. Okay, what am I interested in? I want an assignment that satisfies at least k clauses. Okay, so if I have a matching of size at least k in this bipartite graph, what can you say?
Satisfied.
Do you see that? If there is a matching that's such size at least k, then you can satisfy at least k clauses. Why? Because your matching might be x1 goes to c3, x2 goes to c2, x3 to c7, and so on. So how do I satisfy the k clause?
Edge is will only hit one vertex on the left.
Yeah.
Will only have one. Yeah.
Okay.
So we will take the,
Variable. So
if x1 belongs to C3,
Hmm.
we will take 1.
Yes.
Suppose x1 bar belongs to C3, we will take 0.
Exactly. And that doesn't conflict anything else. So for each of these clauses, I go to the corresponding variable, depending on how it's present, I set it to 0 or 1, I can satisfy that clause. Of course, if I set it to 0, I might falsify something else. In fact, x2 may even have an edge to c7 in the opposite direction, but that doesn't matter. x2 will falsify, but somebody else will satisfy c7, right? So if there is a matching of size at least k, then I can satisfy at least k clauses in this bipartite graph. Good. So I apply my Hall's theorem and find the maximum matching here. So let's call this the G of f, right? So if G of f has a matching of size greater than or equal to k, then okay, I am not actually going to use that theorem, but let's see. Then there exists an assignment satisfying at least k clauses. Okay. So what I am going to show is that we will claim if n is greater than k, then there exists a matching saturating k vertices of x, or there is a crown okay. We will prove this, and then I will also have to tell you, if I have a crown, what do I do with it, because this is a different problem. In the vertex cover, once you have a crown, you can take H and do something about it. Here you need to do something else. Okay, so why do I have a crown? Well, by Hall's theorem, since you do not have a matching that saturates k vertices, or if n is greater than k, then there exists a set S, inclusion wise minimal set, whose neighborhood is small. Right? X has more than k vertices, and it did not give me. Okay, maybe if n is greater than or equal to k, so is it k minus 1 variables? Maybe. If n is greater than or equal to k, either I apply Hall's theorem and get a matching that saturates k vertices, and then I am done for my MaxSat problem, or I am going to show how I am going to get a crown. So Hall's theorem will tell you there is some subset here whose neighborhood is something small, right? So my crown is going to be H is n of S and my C is S and R is V minus C minus H. So why is this a crown, right? So this is my S, this is my n of S and this is the rest. I mean most of the properties are satisfied, it's just since, so there is no, so S is non-empty because Hall's theorem gave me this, so these two sets are non-empty. There is no H from here to here because this is exactly n of S. So there is no SRH. So I just need to show that there is a matching that saturates all these vertices, right? Why is that? Remember, this set S is inclusion wise minimal. That means if I remove some vertex X, then for the remaining vertices, they have enough neighbors here, so there is a matching that of this type that saturates all of these vertices, right? What is its size? So in GSNFS, this bipartite graph, there exists a matching of size cardinality of S minus 1 because it's inclusion wise minimal. But n of S is strictly smaller than cardinality of S. So there is a matching that saturates every vertex of n of S because n of S actually is equal to S minus 1 is what it says you, right? So this is equal to size of n of S because if n of S is even smaller, where can these matching edges go? So n of S is actually equal to S minus 1, size of S minus 1, and there is a matching that saturates every vertex of NS. So there is a crown. Okay, so I proved this. If you have greater than or equal to k variables here, then either I will find a k matching or I will find a crown. Now what do I do with the crown? Well, I will satisfy all of these clauses clearly because I will set the corresponding variables here and I can set these clauses and move on and work with the remaining thing. So without loss of generality, every satisfying assignment, every max sat assignment for the formula will set all of these clauses true. Why? Because there is one way to do that. I mean, if you do something less, I mean basically these variables are affecting only these clauses. So I can set them the way I want to satisfy all these clauses and work with the remaining clauses. So the crown reduction rule also applies here, more or less in the same way as we use for vertex.
Why then, how do you satisfy the S clauses?
N of S clauses. S is the variables, remember. N of S clauses, because of this matching, I picked the corresponding variables. The way I argued, if you have a k size matching, there is k satisfying assignment. I picked the corresponding variable here to satisfy these clauses.
I didn't get the part about maximum.
No. Yeah, I was just saying that if you look at the assignment that satisfies the maximum number of clauses, they should satisfy all of these clauses. So it's like, any minimum size vertex cover should contain this and I am picking it up. So I am doing the correct thing. So that's a kind of argument that, because if it does not satisfy all of these clauses, I have a way to flip these variables to satisfy all these clauses without affecting anything else. So the crown reduction is, the reduction rule is, if we find a crown, set variables in S appropriately, to satisfy clauses in H. So all these classes go away, these variables go away because they don't appear anywhere else, and you're going to work with the remaining formula. And in the remaining formula, now you have reduced the number of variables. If n is at least k, either you will find a matching or you will find a count, keep reducing it. When do you stop? When n has become strictly less than k. So now you have a kernel which is at most 2k clauses and k minus 1 variables. Very impressive, right? I mean, okay, good. So sunflower lemma is one nice combinatorial tool which gave some reduction for heating set, and this crown is another combinatorial tool which gives you a kernel for vertex cover maxat. And okay, next time we will reduce the vertex cover kernel size even further to 2k using linear programming.